Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. This video lecture presents an in-depth exploration of the key role of Max von Laue's work, starting with the historical context, core principles, a comprehensive review, and an intricate conceptual analysis of the X-ray diffraction and X-ray scattering, theoretical as well as mathematical aspects, and how it revolutionized the field of structural biophysics and particle waves. This video lesson is a compact information guide, in the form of your ready exam answer paper. Prior to watching this video lesson here, in order to fully comprehend the relevant background, and to satisfy your curious mind, viewers are advised to watch my earlier video lectures on elaborate conceptual recount of light diffraction and interference, Rayleigh scattering, crystal system, and Thomas Young's double-slit experiment. Please find the links in the description below. As we all know, wave is an undulatory phenomenon, a disturbance so to speak, that propagates through space and time, and is regularly repeated. X-ray is a form of electromagnetic radiation of high energy and very short wavelength, which is able to pass through most materials that are opaque to light, for example, human body, hence widely applied in medical imaging. Crystals are composed of three-dimensional patterns. These patterns consist of atoms, or groups of atoms, in ordered and symmetrical arrangements, which are repeated at regular intervals, keeping the same orientation with respect to one another. Let's start with this most simplified one, a cubic crystal system, with unit cell dimension, A. Here's a non-cubic system with unequal dimensions or parameters. A diffraction pattern is obtained by measuring the intensity of the scattered waves as a function of scattering angle. Peaks intensify as the number of rows increases in a very similar manner to the diffraction peaks from a diffraction grating as the number of slits increases. As you have already learned from my earlier elaborate video lecture, diffraction refers to the scattering of waves around obstacles or apertures, or the spreading out of wave fronts from a chromatographic grating, which results in diffraction pattern. This is what one can discern in the context of Bragg's law. Please note that X-ray diffraction is often considered a subset of X-ray scattering, where the scattering is elastic and the scattering object is crystalline. In order to discern X-ray scattering and X-ray diffraction, one has to relate to the concept of light scattering. Well, light scattering is defined as a phenomenon of deflection or deviation of light beams from its original course of trajectory, caused by irregularities in the propagation. As a result of collision with medium particles and interactions with inhomogeneities in a medium. This phenomenon is responsible for various natural effects, such as the blue sky, white clouds. A typical example is Rayleigh scattering. You must have noticed that I make a point saying Bragg's instead of just Bragg, to show respect for the historic research works of both the father and the son, and their individual contributions. The specular reflection of X-rays. This is the original historic publication of Lawrence Bragg in Nature, back in 1912, still available online for ardent readers. The culmination of structural studies in the history of experimental physics was the historic breakthrough by Watson-Crick double-helix DNA structure housed in the Cavendish Laboratory when Lawrence Bragg was the director of the Cavendish Laboratory, Cambridge. Biotechnology, crime detection, forensic science, recombinant DNA. None of these would be possible if Watson and Crick had not discovered DNA structure using X-ray diffraction. Here you can see that the same portion of crystal lattice can be dissected into atomic planes in different orientations, thereby altering the d-spacing, an angle of incidence, and the direction of reflection. The layers are merely projected onto 2 dimensions, and look like parallel rows. Along the direction x, wave vectors k represent the incident X-rays, as shown in yellow color, and impinge upon the 2 atoms on the aforementioned oblique lattice plane, at an incidence angle theta. On the other hand, along the direction x', wave vectors k' represent the scattered X-rays, as shown in fuchsia color, and are scattered from those 2 atoms at a scattering angle theta'. For now, as a working example, let's consider a one-dimensional row of evenly spaced discrete lattice points of a crystal. Here, as depicted in the diagram, it happens to be a simplified segment of one of those arbitrary oblique lattice atomic planes. on the one-dimensional row of atoms, represented by a series of blue globules, on a virtual crystal lattice plane, incoming beams of X-rays R1 and R2, as shown in yellow color, are incident on atoms A and D at an angle θ0. After getting scattered, beams R1 and R2, shown in fuchsia color, emerge at scattering angle θ. Defined by the wave fronts, the path difference is indicated by the red segments as part of the red right-angled triangles. What we realize is, first of all, no fractional cooperative dispersion orders can occur. Furthermore, provided that this incident angle is maintained constant, this equation would also be valid for any scattered beam that happens to emerge with this same scattering angle from the target atom. What would that imply? What would that lead to? Let's see what it's gonna look like. In multidimensional cases, considering several rows of atoms, in any periodically ordered three-dimensional distribution of atoms, these equations are fulfilled simultaneously, and cooperative scattering from such systems would result in discrete diffraction lines. Therefore, all scattered beams around the row of atoms, with the same scattering angles, would fulfill these equations, and would form a conical surface, coaxial with the row of atoms. Like this.
Ready lecture notes and study materials are available on request. Please use the comment section below for further academic discussions. Viewers' suggestions and ideas of new video lesson topics are gratefully appreciated. Stay tuned for more uploads. Please remember to like, subscribe, share.